We begin in the quiet, an endless, velvet black void, dusted with 1,000,000,000,000 points of light. For as long as we have looked up, we have asked the same, haunting question. Are we alone? This is the grand puzzle, the Fermi paradox. Our galaxy alone should have billions of Earth-like worlds, and it has had billions of years to produce civilizations. Yet, when we listen, all we hear is an eerie, profound silence. It's a silence that suggests we are either impossibly special or terrifyingly late to a party that has already ended. But perhaps we have been blinded by our own cosmic loneliness. Perhaps we are asking the wrong question entirely. The most profound mystery in the universe isn't, where is everybody else? The real riddle, the one that stares back at us from every mirror and every microbe, is this: why are we here? And even more unsettling, why are we here so fast? To understand this, we have to rewind the clock. Not to the first humans, not to the dinosaurs, but all the way back to the birth of our world. 4.5 billion years ago, Earth was not a blue marble. It was a Hadean nightmare, a seething ball of molten rock and boiling iron, shrouded in a toxic atmosphere of methane and sulfur. This was a planet under construction, and the construction site was a war zone. For its first 500 million years, our world was trapped in a cosmic shooting gallery. A relentless downpour of comets and asteroids, the leftover debris from the solar system's formation, hammered the surface. One of these impacts was so catastrophic it vaporized a chunk of our planet, throwing it into orbit to become the moon. This was not a cradle, a warm little pond for life to gently begin. This was a planetary-scale sterilization chamber, an anvil where any attempt at complex chemistry was instantly smashed to atoms. Life, as we understand it, is a miracle of delicate, complex information. It requires a stable platform, a liquid medium, and above all, it requires time. Time for random molecules to bump into each other, to form chains, to learn the trick of copying themselves. The Hadean Aeon offered no stability, no platform, and no time. The planet was repeatedly, violently reset to zero. Then, around 4 billion years ago, the Great Bombardment finally subsided. The surface cooled just enough for the steam in the atmosphere to condense and fall as rain. For the first time, liquid water pooled into vast, dark oceans. And then the impossible happened. The very second, geologically speaking, that the planet was habitable, it was inhabited. In the ancient, weathered rocks of Western Australia and Greenland, we find our planet's first words. They are not scribbles of simple, half-formed chemicals. They are fossils. Fossils of sophisticated, complex, living communities. These are stromatolites, layered mounds built by colonies of single-celled organisms, dating back 3.5, perhaps even 3.8 billion years. Let that sink in. The window between the planet being a molten hellscape and it hosting thriving, structured, photosynthesizing life is just a few 100 million years, perhaps less. This is the abiogenesis window, and it is terrifyingly narrow. The standard model of abiogenesis, the slow, accidental cooking of a primordial soup, requires eons of sheer, dumb luck. It's a theory that demands patience from the universe. But the rocks, our only witnesses, tell a completely different story. They do not show a long, slow, struggling dawn of proto-life. They show a world that was barren, and then, in an instant, was alive. The system already knew how to build cells, how to metabolize, how to replicate. Life didn't crawl out of the muck. It landed, fully formed, and ready to go. This is the great paradox at the heart of our own existence. The textbooks tell a story of slow, gradual, accidental chemistry. But the geological record tells a story of an overnight miracle. It's as if a complex engine, complete with blueprints and a fuel tank, was dropped onto the factory floor before the building was even finished. This discrepancy forces us to challenge our most fundamental assumption. How do you explain a miracle? How does a system leap from dead chemistry to organized biology with no time for trial and error? It's a puzzle that opens a new and deeply unsettling possibility. What if the clock didn't start on Earth? What if life didn't have to learn its lines here? What if life arrived, late for its own funeral, but just in time for ours? So we are faced with an impossible timeline. A planet barely cooled from its molten birth, and a biosphere that seems to have erupted, fully formed. How do we solve this? The orthodox answer is the one we all learned in school. It's the theory of abiogenesis, life from non-life, an event that happened right here at home, in the chaotic and creative laboratory of the early Earth. We call it the primordial soup. It's a beautiful, poetic idea, first imagined by Charles Darwin as a warm little pond. The theory suggests that Earth's early oceans were a rich, complex chemical broth, with a powerful source of energy, a bolt of lightning, the searing heat from a deep-sea vent, or the unfiltered glare of the young sun. Simple inorganic molecules could be shocked and zapped into the complex organic ones that form the building blocks of life. In 1952, Stanley Miller and Harold Urey famously decided to test this. They built a closed system, a glass-and-tube model of the early Earth, and passed electric sparks through a mixture of methane, ammonia, and water. After just 1 week, they found amino acids, the fundamental components of proteins. The experiment was a triumph. It proved that this stuff of life could form spontaneously from the stuff of a dead planet. More recent theories have moved the location, suggesting maybe it all began in the crushing dark of the deep ocean. Here, at the scalding hydrothermal vents, mineral-rich water provided the energy and the crucible for life's first, tentative chemical reactions. Scientists even have a plausible mechanism, the RNA world. This is the idea that before DNA, the master blueprint, there was a simpler molecule, RNA, that could both store information and act as a catalyst to build things. In this model, these ribozymes slowly learned to copy themselves, getting more complex until one day true DNA-based life emerged. This is the Earth Prime theory, a slow, gradual, step-by-step chemical miracle born of Earth's own elements. It is the reigning scientific hypothesis, and it is an elegant, powerful theory. But it has one nagging problem. It still requires time. Time for the right molecules to form, to find each other in the vastness of an ocean, to link up in the right order, and to learn the sacred trick of replication. All while the planet is still a chaotic, violent place. The narrow window in the fossil record just doesn't seem to fit a story of slow, accidental luck. This profound discomfort has resurrected an older, more radical idea. An idea that for decades was dismissed as science fiction. What if life didn't start here at all? What if it was an immigrant? This is the theory of panspermia, which literally means seeds everywhere. It's the hypothesis that life exists throughout the universe, distributed by meteoroids, asteroids, comets, and even interstellar dust. For a long time, this was just a fringe idea. But the more we learn about the cosmos, and the more we learn about life itself, the blurrier that line between science and fiction becomes. First, we now know the ingredients for life are not unique to Earth. They are, in fact, common. When the Murchison meteorite fell in Australia in 1969, it was a time capsule from the birth of our solar system. Inside that 4.6 billion-year-old rock, scientists found over 100 different amino acids. The very stuff of life, the fundamental components of our own biology, are being forged in the heart of asteroid belts and nebulous clouds, and delivered to us postage paid by cosmic impacts. But could a living thing survive the journey? The vacuum of space, the unshielded solar radiation, the cosmic rays, the bone-deep cold. It's the most hostile environment imaginable. Well, meet the poster child for cosmic resilience. Tardigrada, the water bear. These microscopic creatures are, for all practical purposes, indestructible. They can be boiled, frozen to near absolute zero, subjected to pressures that would crush a submarine, and dehydrated for decades. In 2007, a colony of tardigrades was taken on a mission and exposed directly to the open vacuum and lethal radiation of space. When they were brought back to Earth and rehydrated, they not only woke up, they reproduced. Their resilience is a stunning proof of concept. It demonstrates that biology is far tougher than we ever imagined. It proves that the lifeboat for an interstellar journey doesn't have to be a ship. It can just be life itself. Combine this hardiness with the fact that we have found rocks from Mars here in Antarctica. These are rocks that were blasted off the red planet by an asteroid impact and sent hurtling through space to land here. This isn't a theory, it's a known. This is called lithopanspermia, life hitching a ride inside a rock, shielded from the worst of space. It's entirely plausible that a microbe, buried deep in a comet, could make the same journey. So the case is strong. The ingredients are out there. The resilience is proven. The delivery system works. This simple panspermia, a stray microbe on a rock from Mars, or perhaps from a visiting comet, could absolutely have seeded Earth. But here we hit the same wall. A single, frozen microbe, arriving by chance, doesn't fully explain the speed and complexity of what we see in the Hadean Aeon. Worse, it just kicks the can down the cosmic road. It doesn't solve the mystery of origin. It just moves the warm little pond to another planet at another time. It's a compelling idea, but it feels incomplete. It doesn't account for the feeling that Earth's life wasn't just seeded. It was primed. But what if it wasn't a stray microbe? What if it wasn't an accident at all? What if the package that arrived on our barren shore wasn't just a survivor, but a message? What if it was a library? Simple panspermia, a microbe on a rock, is a compelling theory. But it's an answer that feels too small for the question we've posed. It still relies on sheer, dumb luck. A stray rock, from a relatively nearby neighbor like Mars, finding its way here. But what if the sudden, explosive complexity of life on Earth wasn't an accident at all? What if it was an act? Not a divine act, but an act of foresight. An act of engineering. This brings us to our central hypothesis, a possibility so vast it forces us to rethink our entire place in time. Our Sun is a relatively young star. The universe itself is 13.8 billion years old, while our solar system only coalesced 4.5 billion years ago. This leaves an enormous 9 billion year gap in cosmic history. An ocean of first generations of stars and planets that existed, aged, and died long before our Earth was even a cloud of dust. Imagine, in that earlier generation cosmos, a planet that formed billions of years before our own. A first Earth. This world would have had a head start of 2, 3, maybe 5 billion years. Think of what that means. On our planet, it took nearly 4 billion years to evolve from the first cell to a creature that could build a fire and contemplate the stars. What could life achieve with a multi-billion-year head start? It wouldn't just become complex. It wouldn't just become intelligent. It would, given that timescale, likely become something incomprehensible to us. A civilization that had mastered its own biology, its own planet, and ultimately its own fate. A civilization that could read the future, not in a mystical sense, but in the hard mathematics of its own dying star. Because that is the one, inescapable fate of all life on any world. No star lasts forever. This ancient, unfathomably advanced civilization would have seen its end coming. They would have watched, with cold certainty, as their sun began to swell, threatening to engulf their home, their cradle, their entire history. They would have been the first to face the ultimate question. Do we die with our world, or do we find a way for our legacy to survive? How do you survive the death of a solar system? The popular answer is a colony ship, a giant ark to carry survivors across the void. But the distances between stars are, quite literally, astronomical. Such a journey would take thousands, even millions of years. It's an inefficient, desperate gamble, a fragile bottle thrown into a cosmic ocean, almost certain to fail. It's the solution of a young species. But what if you are a civilization that has mastered genomics, information theory, and nanotechnology? You wouldn't send the gardeners, you would send the seeds. This is the hypothesis of directed panspermia. The idea, first seriously proposed by brilliant minds like Francis Crick, the co-discoverer of DNA, is that life may be intentionally spread throughout the galaxy by advanced intelligences. It's not an invasion, it's a bequest. Facing their own extinction, this ancient civilization didn't launch clumsy, life-filled arcs. They launched Genesis probes. Imagine tiny, autonomous vessels, hyper-shielded against the radiation and erosion of interstellar space. They are built to travel for eons, to drift silently through the darkness for millions, perhaps billions of years, waiting for a signal. They are, in effect, a message in a bottle. But their cargo is not a crew of frozen aliens. Their cargo is the code. It's a molecular toolkit, a pre-packaged, fully formed, and debugged genome. It could be a synthetic universal constructor, a biological machine capable of building cells from raw materials. Or it could simply be a vial of complex, engineered DNA, programmed with the fundamental architecture of life, ready to be released into a receptive environment. These probes would be programmed with one simple directive: find a suitable, sterile, young planet with liquid water. Upon arrival, perhaps detecting the right chemical signatures in an atmosphere or the right temperature, the probe's mission activates. It descends, plunges into a primordial ocean, and releases its cargo. It seeds the world. And the result? You bypass the billions of years of random chemical trial and error. You don't need a slow, accidental soup. You don't need lightning to strike in just the right place. The miracle of abiogenesis is no longer a miracle. It's an installation. The software for life is just loaded. Life erupts not because it slowly learned how, but because the instruction manual was delivered pre-written. This is the lost world hypothesis. It perfectly explains the impossible speed of life's appearance on Earth. It explains why life, from the very beginning, seems to know what it's doing. It suggests that our entire biosphere, from the smallest bacterium to you and me, is an artifact. It means our planet was not a cradle. It was an inheritance. If this Genesis probe, this ancient interstellar seed, truly landed on our nascent world, where is the evidence? We are searching for an artifact 4 billion years old. The relentless recycling of Earth's crust, the grinding of continents, the wind, and the water would have erased any landing craft, any piece of exotic metal eons ago. So we've been looking in the wrong place. The probe wasn't the artifact. The probe was just the delivery system. The artifact is the message it carried. And that message is still here. It's inside every living thing on the planet. We are not looking for a buried monument. We are looking for a ghost in the machine. The artifact we are hunting for is the genome itself. This is the operating system for all life, the digital code, written in a 4-letter alphabet, that builds a bacterium, a redwood, and a human. If a hyper-advanced intelligence designed this code, they wouldn't just send it. They would sign it. They would leave a manufacturer's stamp, not on a piece of metal, but within the data itself. This is the fascinating and highly controversial SETI in the genome hypothesis. SETI, the search for extraterrestrial intelligence, has traditionally used radio telescopes to listen for messages from the stars. But what if the most efficient way to send a message across billions of years isn't with a radio wave, but by encoding it in a molecule that is programmed to self-replicate? What if the message is the life form? For decades, biologists were baffled by our own DNA. Only about 2% of our genome actually codes for the proteins that build our bodies. The other 98% was dismissed as junk DNA, evolutionary leftovers, fossilized viruses, and biological noise. But nature is rarely so wasteful. We are now discovering that this junk is, in fact, a vast and complex control panel, turning genes on and off with breathtaking precision. It's the dark matter of the genome. But what if some of it is more? What if, buried deep within these non-coding sequences, there is a pattern, a sequence so mathematically improbable, so artificial, that it could not have been produced by natural selection? This is what a team of physicists and biologists have seriously proposed. A signature, a simple mathematical hello, or perhaps the fundamental constants of their long-dead universe, stamped into the one thing that would be copied and preserved for all time. The challenge, of course, is one of recognition. How would we distinguish an alien billion-year-old message from the complex but natural noise of evolution? We are like medieval monks finding a modern microchip. We can see it's complex, we can see it does something, but we lack the context to understand its true design or its origin. We are just now learning to read our own code. How could we hope to recognize the editor's notes? But perhaps the clue isn't a hidden sentence. Perhaps the clue is the language itself. We're talking about the universal genetic code. This is the software that translates DNA's four-letter alphabet into the 20 amino acids that build proteins. This code is the same for you, for a mushroom, for a microbe in a hydrothermal vent. It is the operating system for Earth. And this code is weird. It is elegant, but it is also strangely arbitrary in places. Yet, when scientists have analyzed its structure, they've found it to be almost uncannily optimized. It's mathematically structured to be exceptionally good at minimizing errors during replication, like a digital checksum in a computer program. It's one of the best possible codes, out of a quintillion possible alternatives. So how did it get so good? So fast? Did this near-perfect code evolve by blind chance in Earth's chaotic oceans in just a few million years? Or is this a sign of engineering? Is this optimized, error-correcting, universal system the engine itself delivered fully assembled? Is this the artifact we've been looking for? We search for alien artifacts, for metal objects, for things we can put in a museum. But the directed panspermia hypothesis suggests we are the artifact. The alien technology isn't a ship. It's the cell. It's the ribosome, the intricate molecular machine that reads the code. It's the DNA itself, a data storage medium so dense it makes our best hard drives look like stone tablets. The evidence isn't out there. The evidence is in here. If the Genesis probe hypothesis is true, if the code for life was delivered, we are then faced with two distinct lines of inquiry. The first, as we've seen, is the software, the ghost in our genome. But the second is far more tangible. What about the hardware? What about the delivery system itself? We are searching for an artifact 4 billion years old, a piece of technology from a lost world. Where is the probe? We can be almost certain it is not on Earth. Our planet is a relentless recycling machine. The engine of plate tectonics, combined with 4 billion years of wind and water erosion, grinds, melts, and buries everything. Any physical artifact that landed on our surface in the Hadean Eon would have been subducted into the mantle, obliterated by impacts, or weathered into unrecognizable dust millennia ago. To find the artifact, we must stop looking down. We have to look up. This is the hunt for the messenger, and it moves our investigation from biology to the emerging field of astroarchaeology. We are not just looking for life, we are looking for relics. We are searching the solar system for the technological fossils of the intelligence that may have seeded this world. We are looking for the smoking gun of our own creation. And on October 19, 2017, something flew right through our solar system that looked suspiciously like a bullet. Its name was Oumuamua, Hawaiian for a messenger from afar. It was the first interstellar object ever detected, and it was deeply, profoundly weird. It was dark, reddish, shaped perhaps like a cigar or a flat pancake, and it was tumbling in a chaotic way. It looked, in short, like nothing in our own solar system. But its strangest feature was its movement. As it swung past the sun, Oumuamua accelerated. It pushed away with a force that gravity alone could not explain. The mainstream consensus desperately tried to explain this as outgassing from a comet, yet there was no gas, no dust, no tail. The anomaly was so profound that it led Harvard's top astronomer, Avi Loeb, to posit the one hypothesis that fit the data. It was an artificial object, a piece of alien technology. The world jumped to the conclusion of an alien spaceship or a scout. But our hypothesis suggests something far more poignant. What if Oumuamua wasn't a visitor? What if it was garbage? Think about it. What would a derelict, billion-year-old Genesis probe, its mission completed eons ago, its power source dead, look like? It would look like a dark, inert, tumbling piece of metal, pushed by the gentle, non-gravitational force of solar radiation. Oumuamua may be the first relic of our creators we've ever seen. This fire-and-forget probe is one possibility. But a civilization so advanced might not just want to plant the seed. It might want to watch the garden grow. This is the theory of the Bracewell probe, a concept for an autonomous robotic sentinel designed to enter a star system, observe, and wait. It would be programmed to watch for the emergence of intelligent life, a silent observer in the dark. If such a probe was sent to our system, where would you park it? Not on chaotic, unstable Earth. You would place it somewhere quiet, stable and permanent. You would place it on the moon. Our moon is a perfect museum. It has no atmosphere, no weather, no plate tectonics. An artifact placed on its surface for billion years ago would, protected from micrometeorites, still be there, waiting to be found. We have, of course, mapped the moon with incredible resolution. But we have been doing geology, not archaeology. We look for craters and rocks, not right-angled anomalies or non-terrestrial alloys. We would, quite literally, not know what to look for. An artifact of that age might be indistinguishable from a boulder to our untrained eyes. We may have already photographed it 100 times. And there is an even better, more clandestine parking spot. The solar system is not empty. It has gravitationally stable pockets, the Lagrange points, where an object can remain in a fixed position relative to the Earth and Moon. Specifically, the Earth-Sun Trojan points, L4 and L5, are the perfect hiding spots for a dormant observer. We have only just begun to explore these regions. We are, in effect, only now checking the dark corners of our own room. This is the case file, a genetic code that appears uncannily designed, an interstellar visitor that behaved like a piece of technology, and perfect, unexplored hiding places in our own backyard where a silent sentinel could be waiting. The traditional SETI program, the Search for Extraterrestrial Intelligence, has spent decades listening for a radio signal, a hello, from a living, contemporary civilization. This is the logic of equals searching for peers. But perhaps that is the wrong model entirely. Perhaps we're not looking for a pen pal. Perhaps we should be looking for our progenitors. We're not looking for a message. We're looking for a monument. The physical, technological inheritance left behind by the very intelligence that lit the fuse on our world. We stand, at the end of our journey, at a profound crossroads. We are faced with two distinct and deeply consequential stories of our origin. Down one path lies the familiar tale: we are a cosmic accident. We are the product of impossible luck, a 1 in a trillion chemical fluke that occurred in a warm little pond, resulting in a triumphant, but ultimately lonely existence. Down the other path lies a story far more vast, more ancient, and perhaps more meaningful. It is the story of a lost world. We must be clear. We cannot, with our current science, prove this second path. We have no piece of a Genesis probe in a laboratory. We have not yet found an unambiguous mathematical signature buried in our DNA. This remains a bold and perhaps unprovable hypothesis. But it is a hypothesis that does what good science should. It fits the facts, and it does so with a chilling elegance. It explains the speed of life's appearance. It explains the prepackaged, optimized complexity of the genetic code. It turns the miracle of life into an act of inheritance. So, for these final moments, let us walk that second path. Let us accept it as a possibility and ask the one question that truly matters. What does it mean? What does it mean for us, for humanity, as we stand on this small blue world, gazing out at the same silent stars? The first and most humbling realization is that we are not pioneers. We are not the first. We are, in fact, inheritors. This entire breathtaking biosphere, every microbe, every rainforest, every thinking mind, is a living artifact, a 4-billion-year-old piece of technology we have only just begun to understand. We are not the authors of this story. We are, at best, a new chapter, written with the ink of a forgotten civilization. This realization also offers a powerful and deeply poignant solution to the great silence. The Fermi paradox, with its haunting question, "Where is everybody?" is answered in the most tragic way imaginable. We have been listening for a conversation, expecting the galaxy to be a bustling city, full of contemporary voices. But what if we are standing in a vast, ancient museum long after closing hours? What if the city is, in fact, a necropolis? The silence isn't because life is rare. The silence is because time is vast, and the lifespan of intelligence may be tragically short. The builders, the ancient minds from that first Earth, are gone. They died with their star, perhaps billions of years before our sun even ignited. They saw their end coming and, in a final, desperate act of preservation, they did not just send a message. They sent the messenger. We are not their contemporaries. We are their biological echo. This redefines our identity. It makes us, in a very real sense, cosmic orphans. We are the children of a parent we can never meet, a creator we can never question, a civilization we can only guess at through the reverse engineering of our own cells. It is a lonely thought, but it is also the very opposite of meaninglessness. We are not a random chemical spill. We are the purpose of a civilization that came before. We are the carriers of a legacy, a life that refuses to bow to entropy, passed like a sacred torch from one dead world to the next. For all of our history, we have looked up at the stars and searched for equals. We have been looking for a partner, an interlocutor, someone to talk to. This hypothesis suggests we have been looking for the wrong thing entirely. Perhaps we should be looking for a parent. We have been scanning the radio waves, listening for a hello, when the message was never intended for our ears. It was intended for our cells. The last will and testament of this lost world is not etched in stone or broadcast on a frequency. It is written in the helical script of our DNA. It is encoded in the intricate machinery of the ribosome. It is the life that animates us. We are the message. We are the living, breathing, thinking remnants of an intelligence that achieved a form of immortality, not by saving themselves, but by sending themselves. And if this is true, our purpose on this planet is not just to survive. It is not just to build or to consume or to conquer. Our ultimate purpose is to understand. Our duty is to read the message we carry in our very bones. We are the universe's attempt to remember itself. The artifact is us. The mission is to remember. When we look out at the deep fields of space, at the light of the earliest galaxies, we are not just looking out. We may be looking back at the era of our own forgotten ancestors. The evidence we seek is not in the sky. It is in the mirror. We are the alien we've been searching for. And we are, at last, just beginning to wake up.